Hi guys, so the next type of differential equation that we're going to solve is homogeneous differential equations. And what that means is these are differential equations that we can write in this form. dy dx equals f of y over x. And the way we solve them is using this substitution that I'm going to explain in some more detail. But first, let's just have a look at some types of homogeneous differential equations. So look, I have three here. Let's first look at this one. This one is clearly in the form dy dx equals f of y over x, because we've got some function of y over x plus some function of y over x. So it's a function of y over x. This one can be written as, and now sometimes in your exam they actually say, show that this can be written in the form dy dx equals f of y over x. And this can obviously be written as, this is an easy one, y over x cubed. So now it's in this form, f of y over x. This one isn't as obvious, but I can certainly write this as, I can say this is dy dx equals x squared over 3xy is actually x over 3y, and y squared over 3xy is y over 3x. And this can be written as 1 over 3 times y over x. Now, if you're not sure about how I did that, just figure it out yourself, but that is correct, because it's x over y is the same as 1 over y over x plus a third y over x, if you like. That's obviously the same as this. So now it is in the form f of y over x. I know it is homogeneous. And this one here, while it's not written as dy dx equals something, I have 2xy dy dx equals something, and if I divide by 2xy, which I'm going to do in a minute, it is in this form. Well, I can make it into this form. Now, one of the ways to kind of, without doing all of this, now obviously if it tells you to show that it is in this form, yes, you have to do all this, but one of the ways to recognize that it is a homogeneous differential equation without going to all that trouble is if you look at the degree. If you look at the degree of each term, if the degree is the same above the line as below the line, and that's actually why they're called homogeneous, because homogeneous means the same. So here the degree is 2 of this term, here the degree is 2, and here the degree is 2. So it's 2 in the numerator and 2 in the denominator. Similarly, if we had something of this like this, dy dx equals x squared over y squared plus 3x y squared plus y cubed over, I don't know, 2x squared y. This, I could write this in this form because I know I have a 2 over 2. This is an x to the 1 y squared, so this is like a degree 3. So it's the degree of the x and the y together. This is degree 3 and this is degree 3. So this is a homogeneous differential equation. Okay, so that's recognizing what we're dealing with. Once we accept that we have a homogeneous differential equation, and by the way, they don't say, this is actually a past paper question, they don't say in the exam, hey everybody, this is a homogeneous differential equation, please use this substitution. Although sometimes they do actually say use the substitution, but they don't always say that. In fact, in this example, they don't say it at all. So you need to kind of recognize that this is a homogeneous differential equation. And the way we recognize it is because I can, as soon as I do this, dy dx equals y squared minus x squared over 2xy, I see this situation where I have the degree in the numerator. The degree in each term in the numerator is the same as the degree of the denominator. Okay, so how are we going to solve it? Well, we're going to use this substitution like we said here. Now, this is not in the formula booklet, so you need to know it. It's y equals vx. Easy. So we go y equals vx, and it's always that. We always use the same substitution. And then we always differentiate this. So the derivative, if y is equal to vx, the derivative is, now I have to use the product rule here because v is a function of x itself. So I have to say v times, or this times the derivative of this, plus this times the derivative of this. So you end up with v times 1, because the derivative of x is 1, plus x times dv dx, because the derivative of v is dv dx. So this is my dy dx. So instead of dy dx, I'm going to write v plus x times dv dx equals, and I'm going to show you why we do this and why the whole thing works, and you'll see it in a second. Instead of y, I'm going to put vx. So this is vx squared minus x squared all over 2x times vx. Now, what happens is, and this is why it works, this is why it works for homogeneous equations, and why I talk about the degree. If the degree is the same, what's going to happen here is the x's are going to cancel, because I've changed the y's into x's, so the whole thing's going to cancel. I'm just going to be left with v's to the right of the equation sign, or the equal sign. So I'm going to cancel the x squared, because I have an x squared here, an x squared here, and an x squared in the denominator. They all cancel. So I'm left with v squared minus 1 all over 2v. So what I have here is now a separable differential equation, and that's the whole point of this. I used the substitution to change the homogeneous differential equation into a separable differential equation. So it's separable because, well, I have this v here, but I can just subtract it from the left here, and that's exactly what I'm going to do. This is equal to, so it's x dv dx equals v squared minus 1 over 2v, and I'm going to, if you allow me to do this, I'm going to subtract v, but because it's going, I'm going to put it above here, I need a common denominator, so I'm actually subtracting 2v squared, because 2v squared over 2v is v. So I'm subtracting the v. I just skipped a step, which is actually minus v squared minus 1 over 2v. Okay, so I've actually chosen a pretty difficult question. This is a difficult question because what I'm about to do now is difficult. The actual separable differential equation is difficult. But the main point of this lesson is to just get to this point that I'm at now, because now it's separable. Look, I can separate this. Let's write this x dv dx equals minus, I'll take out the minus, v squared plus 1 over 2v. So look, I have a separable differential equation, and let's do that. Let's separate the variables. So I have 2v over v squared plus 1, I think I'll leave the minus up here, equals negative 1 over x dx. And I'm going to integrate this is equal to the integral of this. And there we go. Sorry, I should have said dv. Okay, the rest of this is actually a little bit tricky, but the main part of the lesson is to get to this point. Now we're just basically solving a separable, variable separable differential equation. And let's do it. Let's finish it. Now, he says, show that the solution is x squared plus y squared equals cx, where c is a positive constant. Also note that x is bigger than 0. Okay, so there's lots of parts. There's lots of different parts of this equation here, that this integration that I'm going to do that's tricky, including this first bit. So the derivative of this is actually ln of, it's ln of v squared plus 1. The reason for that is if I differentiate ln of v squared plus 1, I get 1 over v squared plus 1 times 2v, which is this. I did that pretty quickly because I know this when I've seen this integral many times. If you're not sure, just use a substitution. I don't want to use another substitution in this substitution because it'll get a bit confusing, but just make sure you know how to do that. Equals minus ln of x plus c. Now, this is, if you haven't seen what I'm about to do here before, you're going to find this a little bit confusing, but normally I add the plus c here. But when there's when there is ln's or natural logs involved, like here and here, instead of putting c, I'm actually just going to put ln of c. Why can I do that? Well, think about it. C can be anything, and ln of c can be anything. So the constant is just ln of c. This is what the constant is. ln of c is a constant. I've put it in that form because now I can nicely do this. I can say ln of v squared plus 1. And by the way, well, let's keep it as v squared plus 1, but v is actually equal to, if we look at our substitution here, v is actually going to be y over x, but let's keep it as v for a second. So I can say ln of v squared plus 1 equals ln of c over x, like this. I can put it in the modulus sign because c has to be positive. Okay, now once it's in this form, I can take out the ln and actually the modulus sign, and I can say v squared plus 1 is equal to c over x. And because the substitution that I used was y equals vx, this was my substitution, y equals vx, so v is equal to y over x. So this is y over x squared plus 1 equals c over x. Now they wanted, let's see what they want. What form do they want? They want x squared plus y squared equals cx. So they want x squared plus y squared. X squared plus y squared equals cx. That's the solution I'm trying to find. So this should be straightforward. It's going to be y squared over x squared plus 1 equals c over x. Multiply across by x squared, and I get y squared plus x squared, oh, I have it, equals cx. So I've shown it. I'm going to write QED. Okay, so look, guys, I am well aware that this from here down to here is not straightforward. That was a difficult past paper question. Yes, I certainly want you to understand each step, but the main part of this lesson was to turn this differential equation that I cannot solve into this differential equation that I can solve by separating the variables. And it's always the same. One, recognize that it's a homogeneous differential equation by looking at the degrees. Then use this substitution y equals vx, differentiate to change dy dx into this, and then break it down into some kind of differential equations whose variables you can separate. Okay, hopefully that makes sense. Definitely practice a number of those types, and I think we have one more type of differential equation, one more technique to solve differential equations. So I'll see you in that lesson.